Today I will be reviewing a paper. You can see it's titled on the slide. It's about the fusion of different neuroimaging modalities in a single deep learning lecture. I think it is mostly interesting because it shows, well, because things on the causes, but also because it is showing interesting way how we can extract new features from the existing neuroimaging data, which I haven't seen before. And also they use it in what they say an interpretable deep learning architecture for graph data. And they show some results that they claim are interpretable. I'm not sure if it is, but it's like 80%. So let's start with the overview of the whole approach presented in the paper. So the authors of this work are working with three modalities: functional MRI, structural MRI, and DTI. So functional MRI gives you a time series of like brain activations. And sMRI is a single three-dimensional image of the brain. It's like high quality. It shows you details on the features. DTI, I'm not actually sure how to explain, so if anyone knows how it works, I'd like to listen. You know how DTI works.
Diffusion tensor imaging. So, well, basically it measures the molecule water diffusion or protons diffusion, how in which direction they move. And like you can wait and see the concentration change, and then you can see, oh, okay, well, in this little cubicle, they're moving more readily. The diffusion movement is happening more readily across this direction than that direction. Well, that means there's a myelinated sheath axon there that prevents diffusion across and favors diffusion there. But then in each little space, we will measure directions of movement. And then the task is computational. So how do we connect all of that? Because now, like, we know there is a line there, but all we do is like tiny aperture. You look there and you see, okay, it's that line, that's that line, that line. Now you have to connect all of this together. That's
cool. And it's important because we are looking for the water molecules.
Well, because we're looking at hydrogen. And we're looking at hydrogen. Hydrogen is just one proton, and yeah, in the water or anywhere, it's just hydrogen has this.
Water's electroaffinity, I think it was.
Yeah, for a second.
It's dipole because it's like shaped like.
Well, water is dipole, but no, like it's just the proton. It's not. I don't think we're looking at water at all.
I think for MRI you're interested in magnetic momentum and dipole is an electric momentum, so it's not.
Yeah. And I was looking at other elements in the brain that are as suitable, and nobody uses much like anything. There's one specific form of carbon, but we have to inject it, and it's like PET is injecting like actual radioactive dyes with a fast half-life.
Okay.
That's as far as I know. I can don't quote me on that. I'm an LLM like everyone else.
Welcome to discuss that. So they are working with three modalities, and they are using them inside graph neural network. We will review what this network is. I think they presented it in a previous paper, so it's not the same for this one. Okay. And finally, they show how they came up with a way how to fuse all those different modalities in a meaningful way inside this difficult. So let's start with reviewing how the model works, and then we will get to how they inject the data and feature engineer new features. And then we will take a look at the results. So let's start with the model. So you saw P6 blocks like this on the previous picture. It's like the main layer of their model. It's a graph convolution layer. This equation shows how this graph convolution works. Essentially, as I understand, graph evolution allows you to scan your graph neighbors of every node do some kind of operation design. So it's like aware of the graph structure and gives you something meaningful on the graph. And connectivity is like a graph representation of a brain. So it's very useful here. It relies on, well, the weights, the node features of your graph. Each node feature is one brain region. You need to come up with a way how to extract those features. Do it. The adjacency matrix is like how many connections are characterized, how many nodes, how many connections each node is having. So how interconnected it is with the rest. Degree matrix, I think what I just said was degree matrix and adjacency matrix and just matrix of functions.
It's a Laplacian, right? There's degree and adjacency. Well, when you multiply by degree from both sides, you get the Laplacian matrix.
Okay. So this thing is, but this is.
Yeah, it looks like a Laplacian matrix.
And the modification to the graph evolution layer is an introduction of like a sparsity mask, which is fMRI by plus. It allows them to like mask less important edges in the data. So the forward propagation is one can be separated in 5 steps. They start with constructing an initial graph using either functional connectivity or structural connectivity features, or by fusing them. I'm not really sure how they do it. They don't really operate. They can make an initial graph. Then they pass it to their model and get some updated node bearings. Then they inject those nodes features with new features extracted from different data. Then they pass it again to the model, then make the prediction. And to train this model, so this model can be trained to do classification or regression. This lecture is describing this. They also have a sparsity objective for their sparsity mask. This thing. So they're trying to make this mask as sparse as possible, and they're using 3 different ways of sparsifying. Like this is absolute, this is squared error, it's like some squares. And this is, I'm not really sure what this is on data matrix. So this is also sparsity check. One more component of that was is the like loss component which wants learning of meaningful graph. And a meaningful graph in their idea of meaningful graph is that node embeddings that are connected in the graph will be similar. And so this, by minimizing this objective, shows what metrics should get more similar in there.
So that degree matrices and times A and stuff, I think it's just algebraic derivation. It's part of weighted graph Laplacian or normalized graph Laplacian. It's not the graph Laplacian. Identity minus the square root of degree. No, the one we were discussing before. But yeah, here, yeah, the actual it's. This is kind of a half-digested, regurgitated version of equation. It's not start of the things. So there is inverse there. Graph Laplacian is weighted graph Laplacian or normalized is identity minus this thing. Only degrees are not inverted. So it's just square root times adjacency times square root. But what is tilde and things like that, I don't know.
So yeah, it's like they're doing some, they added some identity matrix, I think, to make the model more stable. It has something to do with how graph works.
Yeah, okay. Well, anyways,
Essentially it's just, I guess, Yeah, so we talked about training, we talked about the model, how it works. But let's talk about, sorry, one more thing. So they're learning these matrix, these sparsity matrix, and they're using it in their model to mask less important edges. So in the end, once they have trained their model, they can extract it, and it's essentially a matrix of weights. It's a property of the model. So once you have trained your model, you can get this matrix and try to analyze it. And another way to analyze the results is by using just silencing maps. And this kind of also promising because their features are engineered, so they know like what they mean. And they can make some deductions. So we have covered the model. Let's talk about how they do feature engineering and feature injection in them. So they propose to fuse these three modalities in different ways. They propose to extract anatomical features from the anatomical sMRI image. They propose to analyze intrinsic neural timescales, some metric related to how time series in fMRI behaves. And structure coupling, function coupling, is just compares how similar are functional connectivity and structural connectivity analysis. So here are a little more details. So when for the anatomical image for the sMRI data, they propose to extract these kind of features. One of them is related to all sorts of surface morphology properties, volume properties, like a surface area of your gray matter or thickness of gray matter, volume, and so on. And by the way, in the paper, they are giving references to all of those methods, so you can check them out and see how they work if you're interested. Another feature they proposed to extract from the anatomical image is cortical thickness. I'm not really sure how it's different from the first one. Looks like it's also about dimensions, but it's also a different reference. It's yet another approach to feature engineering. And finally, they suggest to evaluate the curvature of the brain regions. I guess another thing they hope to extract from fMRI is intrinsic neural timescales. So it looks a little artificial to me, but from what I got, it's like a way to evaluate the autocorrelation of your time series, like for how long it stays autocorrelated. And based on that, you can assign some score to it from 0 to 1. And based on that, you can get a picture. Do you have any questions? And finally, the third feature they propose to extract from functional connectivity and structural connectivity is the measure of similarity of those connectivities. So they're taking each row, each row as an embedding for each node, and they compare the Spearman-Bragg correlation. It's like it compares how arranged, how synchronized two arrays are, suppose how many permutations you need to make with one and another to arrange them, like increasing order, for example. Yeah. So this is another way how to extract features from connectivity. And so they're showing the results. First, they have compared the performance of their model on different modalities, different combinations of modalities. And they also compared how different architectures work with their features and techniques for feature treatment. So what they found is they found that fusing modalities together inside their model gives them a better score. So they're comparing prediction of some cognitive scores, 3 types of them, crystal, fluid, and total. They're somehow different, and you can either regress them or put some threshold and do classification. And so, yeah, they're showing that the regression is improving with more modalities. And it seems like the architecture is kind of better than others. But I guess the interesting thing is their method for feature engineering is very reusable. They were able to inject it into those models, even though they are not their models. So that's kind of interesting. Another thing is their interpretability results. It's these learned sparsity matrix. So they analyze it too, and I'm not sure it doesn't look very interpretatively sparse. They see kind of clusters, but you can get another side list.
So are these the masks that they found for different modalities? Or is it the fused mask?
It's a single mask for all modalities. And it can be learned from any combination of forms. So in this case, they use all modalities to get this mask. Yeah, there is this mask. It's a sparsity mask. It's a single learning mask that you can extract from your model and try to analyze it. I'm not sure if this is going to be helpful, but there is a bit. And finally, they analyze the feature importance for classification and regression of cognitive scores. And they found that you can find more and less important features using science maps, this kind of thing. And in this case, they found that for some reason, from what I see, it seems like structural features, everything here, except for the last two, are less important. And autocorrelation of fMRI isn't important, but the coupling between structural and functional connectivity is important. So, in another case, the autocorrelative property of fMRI turned out to be important than other things. So, and I guess to summarize all short. So the paper proposes a way how to feature engineer new features from different neuroimaging modalities. I think it's an interesting example how to do this. I want to try it with my data. Hope it was interesting to you. Do you have any questions? Do you want me to go back to it?
Question on the previous slide, is that also including the DTI? That was just FNC, sorry, the functional connection for the fMRI structural, right? Yeah, you said this isn't including all three.
Yes.
It's okay, sorry.
Yeah, so these things on the x-axis, they are objective features. They're showing how important these features are for classification or regression process later. I'm seeing this result that structure functional coupling is kind of important, and I suppose it's maybe an artifact that just FNC is super predictive. Structural connectivity is super predictive.
Did they do this for like one fixed sparsity level, or did they try multiple data?
I don't think they set any sparsity level. They have their sparsity objective to minimize, to mask as many unnecessary connections.
But you have lambda 1, 2, 3, right?
Yes, different ways for different ways to measure sparsity. This one is like our sound, this is square sound, and this is something else.
Yeah, isn't like the sparsity level? Well, the sparsity level is 1 if you think about here, right?
No, I was thinking about like sparsity, especially.
Well, so you have this mask.
What I see this objective is trying to maximize the sparsity as much as possible, so it doesn't have a great threshold. It will balance itself with the other host components.
Well, so the sparsity is as important, the sparsities that they are using. Well, okay,
They use sparsity because they have this mechanism for sparsity mask. So if they train their model to learn this sparsity, it should mask less important edges. Then they can analyze this sparsity mask and work the conclusions.
Yeah, but this M is quite weird. If you look at the objective again, L1 promotes sparsity, L2 promotes density, and I'm trying to analyze this. So L2 promotes distribution of energy everywhere. So it's every value of M has some value. That's what L2 promotes. This one,
Yeah, but still it promotes minimizing those values. Yeah, they can be more spread around.
yes, spread around.
It's
It's not sparse. It's dense. I think given energy, it will try to smear them around.
I guess I don't know if I mentioned it, but this sparsity mask, it's like a mask between fields at once. So
Yeah.
you multiply it, and it's like a gate, which allows some edges to work.
Yes,
And
yes.
so if you train your sparsity mask to be as sparse as possible, it will mask less edges.
Yes, but that's not what loss is doing.
The mask can have only 0 or 1 elements.
No. It's a gate. It's a continuous between 0 and 1.
Oh,
It's like a sigmoid.
But this component, it seems like some.
But like this promotes sparsity. This promotes density. This wants all values to have all elements to have value. Favors all elements. Favors the cases when all elements have equal values. That's the best. This favors the cases when fewer elements have values, mostly zeros. This, can you comment on that, please? Or
So from what I see, this identity matrix is removing the diagonal ones. So I guess it's trying to minimize of the diagonal elements.
with the same M transpose, so is the graph symmetric originally? Is M symmetric? So M is already symmetric, and then you're doing M transpose. So it's essentially this is M squared, right? You're
Yeah, I guess it's
squaring the string, like counting or turning into path of length 2. So you're looking at the path of length 2, and you're saying, oh, okay, those path of length 2 should exist everywhere, because you're doing again Frobenius norm. So second order, you're promoting density here. The fact that you're subtracting the diagonal self edges means loops of length to self loops of length to don't matter. Don't set them or don't.
I'm not sure if I agree with you about like that it's promoting the density.
No, L2 promotes the density. You
Well,
can just
like I think it's promoting the solutions that are more dense, but in the end, this is a sparsity matrix. It will try to minimize the weights.
solutions are M. M are the solutions for this because parameters of L2. So L2 is a function.
Yeah.
And input is M. If you flatten M into a vector, L2 is minimal, like when everyone has the values, right?
But it also means they are all zeros. So it's a sparsity.
No, all zeros is not the sparsity that we are interested in.
Well, yeah, but all zeros won't be achieved because there are other components that have their own classification points.
No, L2 is completely opposite to sparsity. It's actually density, if you think about it.
Okay.
It's like if you have a budget on values, like say total sum of M is 3. L1 will say, okay, put 3 into this corner, one element, and I will be the happiest. And L2, the one I'm pointing at, will say, divide 3 over all number of elements in M and put them everywhere, and I will be the happiest. That's density. Dense everywhere. Yeah, the value is divided, but everyone has a value. So they're conflicting. They're pulling in a different direction. L1, the first one, is trying to concentrate. L2 is trying to like, okay, we end
I
up.
think one of the reasons why they didn't use like only one component is because they were trying to just as many ways to slice matrix into points.
But this is not specifying. That's my problem.
But yeah,
And if they're learning lambdas, then that's like okay. That's on top of that. What is it that they set it?
I don't remember what
Hyperparameters. So you have sparsity. Like I'm just trying to interpret. I'm just inviting everyone to read what's written actually.
IQ is just taking away the predicting the cognitive scores, right? Is IQ just the cognitive scores?
Yeah,
Okay.
they're training.
No, those the LE.
Oh no, IQ. I have the on lambda 3 after that. I was just curious what that parameter was referring to.
Oh, I thought it's identity matrix. I don't know why Q is there. Yeah, I just interpreted it as identity.
Yeah, Q is the number of nodes. It's like identity matrix with Q. Rows and columns. It's just size.
But it's the same size as M.
Yeah.
And it has to be. Yeah, so it's identity. So M transpose, because M is symmetric, is just M squared. M squared will be non-zero where there is a path of length 2 from edge I to edge J. So if there is a path of length 2 from edge I to edge I, you're subtracting it. You're saying it doesn't matter. Don't try to come back. Don't try to guarantee that there are those paths, but try to favor a loop path of length 2. That's my interpretation of the last. I don't know if they talk about it at all or not, but my interpretation of it.
Time, I guess we can take that.
Yeah. Yeah, if you go to that mask thing.
Information to also the water to some mask.
It's just that funny that they say L1 promotes sparsity and L2 doesn't. It's L2. It's opposite.
Doors.
I don't like maybe I don't see how that last one is also normal. Like symmetry would be more enforceable as a constraint after each iteration. M equals M transpose. You just reset. Also, orthonormality is usually forced like that, or you have to optimize on a Stiefel manifold, etc., etc. I don't see how this where IQ is the identity matrix with inertial matching with the mask M and regularization parameters. They don't look like regularization parameters, but again, furthermore, the regularization term associated with orthonormality. Structural integrity. Well, anyways,
Did you say something else?
symmetry. Yeah, well, I didn't say anything. I just read what they say. They
force symmetry by learning, but it's
yeah. So then you do this every time, right? Every time after the iteration, you recompute M as this.
so you compute E, and it's just
Well, you have to do it every iteration, so you keep M symmetric. I'm trying to interpret equation 7.
So I
Why?
think for the part 3, why they're doing M times M transpose minus I, because if they're both orthogonal matrices, M times M transpose would be the identity. So they set that to 0. So I think minimize that part.
Mhm.
So I guess they want them to be orthogonal for some reason because like each vector captures something.
Yeah, they talk about the I don't see. Now I see how it works.
The second part, I don't understand the lambda 2.
We can talk also about the manifold components. Supposed to promote the graph structure. I wonder how it works. Can I scroll up?
Mhm.
So it's about this. This.
Well, to understand this, you need to understand how graph of Laplacian works. I think that's just too long to explain.
It's like characteristic of a graph, which measures adjacency.
But eigenvectors of graph Laplacian are aligned with the edge structure of the graph and with the smoothness of the graph. So if you take correspond of a graph that corresponds to your lowest eigenvalue, not the highest one, it will be the most smooth one. Like
So
if you
what is eigenvalue of a graph?
eigenvalue of a graph Laplacian. Graph Laplacian is that matrix L. It equals one identity minus adjacency. As a so if you take eigenvalue decomposition of a graph Laplacian, graph Laplacian has n by n dimension, where n is the nodes, and the connection structure of the nodes is represented by edges in the adjacency matrix that went into construction of the graph Laplacian. Now, if you take eigenvalue decomposition of that n by n matrix, where n is the number of nodes, you will get an eigenvector with n values. Take the eigenvector of graph Laplacian and plot those values on the graph as a histogram, as a color map, as something. But take the eigenvector that corresponds to the lowest eigenvalue. And that eigenvector will give you the manifold, the maximum smoothness on this manifold. Not the maximum will be just the constant, but the next maximum smoothness on that manifold. So if you take a ball, for example, and this ball is like a sequence of subdivision of icosahedron or something like that. It's a graph, right? It's a ball made of triangles. You take this graph, construct this graph Laplacian, do eigenvalue decomposition of that L matrix graph Laplacian. Take the graph vector that corresponds to the lowest eigenvalue and plot this graph, and you see that half of the ball will be negative, half of the ball will be positive. It's like a smooth dipole in a sense. Then you go next, highest eigenvalue, the opposite to PCA, what we're doing in the other direction, and you take the graph eigenvector, and plot it again, and it will add frequencies. So it will keep adding frequencies. So those frequencies are geodesic. That's like with respect to the graph, they call it manifold, but it's just like a geodesic, basically smoothness. So smoothness with respect to the graph.
This means this the
Yeah, smoothness means that if you have neighbors, your neighbors are not too different from you. Yeah. Take Lipschitz, take others, like whatever that you define it. You can define smoothness, how much different or how much different is too much. That's smoothness. So
that was 50-50? In your analogy, so we're saying 50-50. That's smoothness, right? Because it's only
yeah, like everything is flat, but then it has to change. Otherwise, it's all constant.
Yeah, otherwise
it kind of flows. Yeah, 50-50. It kind of flows, negative flow into positive slowly. It's not. It wouldn't be colored. Just like this is not. The equator will not be smooth. It will be like a gradual transition from.
yeah. Otherwise, it's not circle.
There are lots of in the what is it, geometric deep learning. They have a lot of online a lot of examples where they take, say, a figurine of a person and do graph Laplacian and plot those vectors with red and blue. Then you see how frequencies are either spatial frequency, but smoothness with respect to the graph. The ball is easy because like it also has geometry. But if I can jumble and mix all the nodes, it still has the geometry of the graph. Some nodes are closer together and some are farther, that you don't have a 3D representation. You can't look at it as a flat smoothness. But what you want is, okay, if you have neighbors, they should be similar to you. That's what they're enforcing practically. But neighbors on the graph. And the graph is also modified because L should be connected with M, right? Is L modified by M? Because if L is not modified by M, then this whole sparsity thing is
don't think it is. So it's like
so the graph is non-sparse. Kind of.
I guess L is here, but it feels like L is fixed. It doesn't really change because of that. It depends on adjacency values.
But where does adjacency come from? Adjacency comes from M, right? From the mask.
No, it comes from data. They derive it from the functional connectivity and structural connectivity.
But functional structure connectivity, everything is connected. It's a fully connected nature.
Yeah, and also they have this fast thematics which disables some edges. But I guess it doesn't affect.
So it doesn't affect the smoothness then. It's kind of decoupled. That's weird. Okay. Okay.
They do a lot of optimization. I guess they have their own ways to make it work the way the quantum plans. For example, simply linearize it this or same way I did
yeah, density matrix is important. That's understandable because then you get a non-invertible matrices and things like that. If you don't do this regularization of eigenvalues.
I think actually the manifold loss does depend on the age, because in
But
equation
H is the
4,
data. You want the data, right? You
but
want
H is masked in equation 4, and then that's used as input in equation 6.
no. It's an embedding, no.
Like equation 4, the output is H,
Yeah,
which is
it's not
after
embedded.
the mask is applied, right?
It's the values, node embedding. So it's the values of the nodes.
Yeah, but the values of the nodes are
At the
affected by
mask.
this plastic mask. So in the end, this thing also depends on the mask.
Mm.
Well,
Okay.
Laplacian doesn't, but H
Yeah,
does.
yeah. But what you want H to be smooth with this, you want it to be smooth with respect to L, with respect to the graph encoded by Laplacian. Okay, anyways, we're partially guessing here to fill in the time of a short talk. Anyways, any other questions or comments on Pavel's talk or on anything?
To summarize, it's just an interesting way to data fusion. You can use some.
Yeah, sounds good. Sounds good. Okay. Nothing. Okay. Yeah, fun paper. Thanks for sharing, Pavel. That's what TJ is saying. Yeah. Good, and we turned on the microphone this time, so. Yeah. Thanks, TJ, for joining, and thanks everyone for watching the art.